Okay, out of all the lessons so far, I'm afraid to say this one's probably going to be the most important. It's also going to be the hardest to start to master because there's a lot of things going on. What you'll find probably is that it will take you a while of feeling like you're hitting your head against a wall, simply because what you're going to have to do is build up some long-term memories with this stuff so that your working memory isn't focusing so hard on some of the basics. But at the beginning, you're going to need to get to grips with the basics as well, which will mean that this whole thing really does feel like a lot. It's akin to weightlifting, essentially. The more you do it, the more you will build strength in it, and the better you will get at it. There's no better thing for calculations other than practice. What I'm going to do is I'm going to give you one really big full example, going from really recapping everything that we've done, and giving you the rundown of how to work this molar calculation. So what we're going to do is we are going to look at the reaction between methane and oxygen. So methane is our simplest hydrocarbon. It is CH4. Now, what I want to do is just recap Lewis structures again. So that central carbon has 4 electrons in its outer shell. Now, if I take us a step back here, we've got C carbon is in group 4, its valency is 4. Hydrogen's in group 1, its valency is 1. And we can switch those numbers over to give us CH4. So that's how we got there. If we wanted to show this as a Lewis structure, we would have 1, 2, 3, 4 electrons for our carbon. 1, 1, 1, 1, 1, and 1, 1, and 1. And this would give us our Lewis structure, sometimes called a dot and cross diagram, of our methane molecule. And this molecule here is on a 2-dimensional plane. We could draw it in a 3-dimensional plane with our dotted line, dashed line, and our triangle. And that shape is a tetrahedral. Now, one of the other things that we want to cover is oxygen. Now, oxygen, you simply have to remember, is a diatomic element, so it will come as O2. And our Lewis structure for this, always aggravating doing oxygen because we've got our circles have kind of been used up already. We've got 1, 2, 3, 4, 5, 6. Now what you'll notice is I didn't do that the right way round really, but I know that I'm going to have to make a double bond here, so I've put these two in the corner. Once again, a little bit of cheating, you might have to do it the full way and think through it first. And with this oxygen, we've got 1, 2, 3, 4, 5, and 6. Now I didn't have to cheat with that one because that atom was orientated on the right hand side, so I could keep going round in a clockwise direction. Once again, just takes practice. Just takes practice doing that. So what we've got is we are going to have a bond here, and we're going to have a bond here. And this is not an acceptable Lewis diagram at the moment, but it's shown me how I need to line this up, and I need to line all of these up so that they are paired up in the center. So my oxygen will have one X, one triangle, another X, another triangle in the center there, and I'm going to have my other electrons at the back here. Admittedly, these ones are a little bit harder to draw as dot and cross diagrams, but I haven't seen them actually come up very often, to be quite honest. And that's showing us a double bond there, and that could be drawn like that if you wanted to, and that gives us our O2. So that molecule there would be linear, and that covers quite a lot of the stuff we kind of chatted about a week or so ago, and really, if you can deal with that stuff and you remember it, that's good. If you don't remember it, take a little look back at those videos and remind yourself. It is going to be easier if you've got as many of the bits of the puzzle as possible before we start. Right, what we're going to do is we are going to react our methane molecules with our oxygen molecules, and we are going to see a reaction. Okay, so this is our equation for the combustion of methane. I've got CH4 here plus O2 gives me CO2 plus H2O. Now, when you see one of these equations in chemistry, the first thing that you have to ask yourself is, does the numbers of all the atoms of each element on this side equal the numbers of each element on this side? What I mean by that is, I've got 2 oxygens here. Do I have 2 on this side? Well, no, I don't actually. I've got 4 hydrogens here. Do I have 4 here? Well, I don't. Now, the first stage to really any question at all is to decide that. Sometimes they will give you it balanced. Some are balanced without having to try, and then there are ones like this where they will give you the equation and you will have to figure out that you need to first balance it, then move on. So the way in which you balance these equations, and I want you to do this method each time, simply because if you don't use this method, you can run yourself aground of not really knowing how many you've counted, how to go about it. This method allows you to order your balancing in such a way that mistakes are minimized. And if you can use any method for doing this. You could do it randomly if you wanted to, and you would still technically be able to manage it. However, a lot of the time you can run aground of making not even a mistake, simply balancing something in the wrong order, because as you can see, we've got elements that are grouped together, and when we multiply this section here, everything within that molecule will be multiplied, but I'll explain that as we go along. The method I want you to use is you will order the metals first, then you will order the non-metals, then you will order the hydrogen. The last thing that you balance is oxygen. So that's the order of thinking about balancing things, is metals, non-metals, hydrogen, and oxygen. And I'm going to use that method to do this one. Now, this one doesn't have any metals in it, so I don't need to worry about the metals. What I'm going to have is the same order of this on this side as well. So I'm going to have M, NM, H, and O. Now, if I had more than one non-metal, doesn't really matter how I order it. All I would do is I would have those written out, and we will have examples of that later on. So, I don't have any metal elements in this equation whatsoever. The non-metal elements I have are carbon. So, the carbon that I've got on both sides, I have one carbon here and I have one carbon here. So that is going to remain 1 and 1. Then the next one that I want to count is hydrogen, and the hydrogen is 4 on this side. So that is H4. There's 4 atoms of hydrogen. I'll just write a 4 there. On this side, there's only 2 hydrogens. So I'm going to put a 2 there. Now, all I'm doing is converting this information up here into a simpler format down here. It's just so I can read it easier. That's all that that's there for. The oxygen is 2 on this side, and it is 3 on this side. Now, the first thing that I want to do is go back down and see which ones are not balanced. So the non-metal carbon is balanced. I have 1 on this side and 1 on this side, so I don't need to worry about that at the moment. The hydrogen is 4 on this side and 2 on this side. So I need to make sure this is balanced. Now, I'm allowed to multiply entire molecules. So I can decide that I will have 2 of that molecule, 3, 4, 15, it doesn't matter. Now, if I want to convert 2 into 4, what do I have to play with on the products side? Well, I've got carbon dioxide. There's no hydrogen in that, so playing about with this is not going to fix my hydrogens. I also have a molecule of water that does have hydrogen, so playing about with this can help me balance this equation. Now, what I'm going to do is if I multiply that whole molecule by 2, what this is going to do is give me 2 H2O molecules. So if I've got 2 H2O molecules, I'm multiplying everything within that molecule by 2. So the number of hydrogens I have now is 2 times 2, which is actually 4. So I take that number out and put 4 there. Now I've got to be careful because I'm not just multiplying hydrogens, I've got an oxygen here as well, and that is part of this multiplication. So I've gone from having 1 oxygen to having 2 oxygens, and you can see that by how many oxygens I've got with 2 molecules of water. So I've got 2 oxygens here, and now I've got 2 times 1, which is 2. I've got 2 oxygens here. 2 plus 2 is 4. Now, the last thing that I've got to balance is oxygen. So I've got an oxygen on this side, and I've got 2 oxygens. I've got oxygen on this side, which is 4. Now, if I play around with that, I'm not going to change the number of oxygens. If I play around with this, I certainly can change the number of oxygens. Now, I want 4. I've got 2. I'm going to have... This is my molecule of oxygen here. So I really need 2 of these to get to 4 atoms of oxygen. So all I need to do is put 2 there. 2 times 2 is 4. Change that to 4. And that is my balanced equation. So this equation has now been balanced by putting a 2 in front of the O2, meaning that there's really 2 molecules of this. Actually 2 moles technically, but we'll get on to moles a little bit later on, and we'll talk a bit about that. So this is really a ratio. So for every 1 of these molecules, I've got 2 of these molecules. More correctly, for every 1 mole of this methane, I've got 2 moles of oxygen. For every 2 moles of oxygen, I produce 1 mole of carbon dioxide and 2 moles of water. That's how you balance these equations, and we're going to move forward and we're going to see if given certain numbers I can actually work out how many grams or how many moles of these that I produce in the end. So this is our theoretically balanced chemical equation, and the ratio is 1 to 2 to 1 to 2. So that is my molar ratio, and we're going to have to use this molar ratio going forward. Right, so the next little bit is going to take us a little bit of time to talk through, and it's going to be important for your understanding. In terms of all of these terms, the most important is actually moles, really. However, the understanding of what a mole is at this stage in your understanding is probably the least important. Understanding the mass, RAM, and GFM of a molecule is probably more important at this stage. Just to go over what a mole is, we essentially work in molar ratios. It's because when we do a reaction like methane plus oxygen, we in real terms couldn't ever take one molecule of methane and react it with one molecule of oxygen. We would have to take a large number of atoms. The mole is really a way of relating the total number of molecules that you have, or at least the total number of protons and neutrons you have, and relating it to mass. Now, what I essentially mean by that is if you take the element hydrogen and you have essentially just got one proton and one electron, that electron has no mass. The mass of a proton is extremely tiny. So tiny that it's very hard to measure. However, if you multiply that proton by 6.02 times 10 to the 23, you will get 1 gram of proton. And that's really what a mole is. It's just a useful thing so that we can use grams, and we can talk about grams, and we can use that molar ratio. So in the last section, we saw that we had to balance this equation, and I said that these were molar ratios. Essentially what that means is you've got 1 mole of methane, you've got 2 moles of oxygen. Now, the understanding of that at this stage isn't actually critical. You're going to be able to do these calculations without fully grasping what a mole is. But if you just think about a mole as not the thing under the ground, but something that relates the scale of atoms, and it allows us to work with enough atoms that we can work in grams easily. That is probably enough for the time being. And that if you've got a certain number of protons, then you've got 1 gram, and that's how the mole really relates to mass. The relative atomic mass is another one that we need to talk about, and I'm actually gonna I'll put in a little box an important little note. So this is the relative atomic mass. Now, you will find this in the data booklet, and we are going to take a look at the data booklet, and we're going to talk a little bit about what we see there. Right, so now that we're talking about
looking at the relative atomic mass. The data booklet's really key for this. So if we scroll down, once again, you will need to use this in the exam, and it's really important that you get used to it. We are looking for the relative atomic masses of our different elements, and that is on page 7. So we'll just scroll down to page 7, and we've got this, which is basically a massive table of most of the elements, and the thing that we're interested in is the relative atomic mass. This is basically the number of protons and neutrons added together that you're likely to find in the nucleus. Now, if we scroll down to, where are we? Copper, and we take a little look at copper, which I did find, there we go. It has a relative atomic mass of 63.5. Now, this does not mean that there is a half a neutron or a half a proton in the nucleus. It is actually 63.5 because half the time you pick up a copper atom, the relative atomic mass will be 63. The other half of the time, it'll be 64. And I'll explain that a little bit further when we switch back to the paper sheets. But it's enough to say that this goes back to your isotopes and the different isotopes you can find. So the number of protons really gives you the element. The number of neutrons can vary, and the element will remain the same, but we say that they are different isotopes of one another. Right, so that is our sheet. The ones that you really want to concern yourself with for the question that we've got is carbon, which has a relative atomic mass of 12, hydrogen, and it's all in alphabetical order, so if you can sing the alphabet song, you can work this. And we were also taking a look at oxygen as well. So these are all your relative atomic masses, and you should have access to the data booklet either through Teams, it should be in files in Teams, or failing that, you can actually look it up on Google as well. Right, that is this bit, and I'll give a little bit of a further explanation about those isotopes.
Okay, so we took a little look at copper specifically in that example, and what we've got with copper is this relative atomic mass that has a 0.5. Now, that doesn't mean that we've got half an atom somewhere. That is just not how we deal with chemistry or reality. What we're actually seeing is if we took a little piece of copper with 10 atoms, then we would find that 1, 2, 3, 4, 5 of those atoms actually had a relative atomic mass of 64, and the other 5 would have a relative atomic mass of 63. Now, if I was to take the two different ones that were there, because they're in equal ratios, I could add them together and then divide by 2 to get the average mass of that copper. And what we're seeing there is the average atomic mass of any given copper atom. So if you were to randomly select an atom, you would get every second one would be 64 and every other one would be 63. So this gives you the average that we've got in terms of your atoms that you're going to find. So you've got a 50% chance of picking up a 64 atom and a 50% chance of picking up a 63 atom. And so when we do the calculation to do an average, we get 63.5. They have actually asked you to do this in the past in the exam, and what they do is they give you an equation and you basically got to plug in the numbers into the equation and get the relative atomic mass out of it. Now, the addition of all the relative atomic masses within the molecule will give us the GFM. So for the GFM, I'm simply going to use our methane molecule, which was CH4. Now, if we go to the data booklet, what we'll find is that carbon has a relative atomic mass of 12 and hydrogen has a relative atomic mass of 1. However, what we'll see here is that we've got actually 4 of those hydrogens. So we need to multiply that by 4 and add these together. So what I've got is 12 plus 4, which gives me 16. So the GFM of our methane molecule is 16. If I was to do that for the oxygen, which was O2, that would be oxygen has a relative atomic mass of 16, but there is 2 of them. And so my GFM for oxygen would equal 32. Now this is going to be important later on, and it's going to feed into our ability to calculate either the number of moles or the mass that we've got. Okay, now this is a fairly classic question, and once again we're sticking with our methane and our oxygen, and we're going to chat a little bit about how we do this. So the first thing to realise is that you're being asked about a calculation question, and all the equations for calculations are actually found in the data booklet. So it's really worth us going and looking at what we have in the data booklet. So this was the equation that we saw in the data booklet, and N is the symbol for moles and the unit is MOL. M is for mass and the unit is always in grams, and if something is given to you in kilograms you will need to convert it into grams. We will do a couple of examples that are a little bit trickier than this one later on, and GFM is our gram formula mass. So this is really where you've got to take your time, think about it, and lay it out in whatever way helps you the best. I'm going to show you the way that I do it. It's up to you whether or not you use this system. Some people that are really confident with maths will take this in their own direction and they'll build up their own understanding of it. If you're not and you need a system to use, I think my system's fairly robust and it's quite easy to follow. So really what we're being asked is, how many grams of oxygen do we need? And to talk about that, first of all, we need to look at our chemical equation again.
Okay, so whenever you come to a calculation question, it is a very good idea to take a look at the data booklet. If we scroll down, it is this first page that's got all of our relationships or equations for chemistry. The one that we're interested in is moles equals mass divided by GFM. Now, what I'm going to show you is how to convert this into a triangle if you don't like rearranging equations, but all the equations that we use are given to you, so you don't actually need to remember them for the exam. You can just look them up in the exam, but you do very much need to know how to use them, and that's a really key point. So I'm going to show you this one and how we use that to really answer our question about how many grams of oxygen we need.
Now, because we worked this out earlier on, I'm not going to go over it too fully. However, what we had was an unbalanced equation and we balanced it using that method. To get these questions right, you need to make sure that the equation that you're actually given is balanced before you start. So, what we've got is 1 mole of CH4 plus 2 moles of O2 would give us 1 mole of CO2 plus 2 moles of H2O. Now, that I like to refer to as the theoretical balanced equation. So this is the theoretical balanced equation. Now, what we're going to do is we're going to convert this into the actual balanced equation. Now, in the question, we were told that we had 12 grams of methane. And we saw in our data booklet that our equation relating moles to mass and GFM was this. Now, what I'm going to do is I'm actually going to convert this into a triangle. The triangles are really just there to help those who struggle rearranging equations. The ability to rearrange equations isn't needed if you use the triangle. It's essentially, if you're struggling with maths, it's a way around balancing those equations. So, we get our triangle in place, and it looks like this. Now, the mass goes on the top, and the number of moles goes here, and the GFM goes here. Now, if you have the chemical equation and you've got a data booklet to hand, you always have the GFM. Now, the GFM for our methane, we already worked out to be 16. Now, the mass itself is given to you in the question. They might have decided to give you the moles. They might have decided to give you the mass. They can decide what they give you, but I've ticked off the ones that I've been given, and we were given 12 grams of methane. Now, the number of moles is then simply calculated by 12 divided by 16. It's a good idea, if you don't have one already, to get yourself a scientific calculator. These ones basically make sure they basically do BODMAS internally, so you don't need to worry about doing BODMAS every time. They are worth the investment. So we've got 12 divided by 16 and 3/4. I don't want it in fractions, I want it in decimals, so that equals 0.75. So that equals 0.75 mole. Now that's how many moles of this I've got, and I'll write that up here. 0.75. This is the actual molar ratio. So we might call that the, right, I'm going to take that away. I'm going to write the theoretical molar ratio. So our theoretical molar ratio is 1 to 2 to 1 to 2. The actual molar ratio will follow the same pattern, however the numbers are going to be slightly different, because I don't have 1 mole of methane. I've got 0.75 moles of methane. However, the ratio is still 1 to 2. So what do I have to do to that number to find out how many moles of oxygen I need? Well, I simply have to multiply it by 2. So 0.75 times 2 is 1.5. And I will always do it in my calculator, even though it's fairly straightforward. You don't want to make a silly mistake. So my actual molar ratios are 0.75, 1.5, 0.75, and 1.5. And that is derived from the theoretical molar ratio, which was 1 to 2 to 1 to 2. These are the same, but the numbers are different. So this is a simple whole number ratio. These are the actual ratios of what I'm going to get are. Now, the question originally was, if we were given 12 grams of methane, how many grams of oxygen would we need? So what we've done is we've used that 12 grams to work out how many moles of methane we had. And because we'd balanced the equation, we got the number of moles of oxygen we have. But we're not being asked for the number of moles of oxygen, we're being asked for the mass. So once again, we're going to use this, but we're going to have slightly different information in it. So what we've got is we have, once again, I'm just going to start with the triangle. I'll put it down here this time. I'll try and keep it all on the one page. You might want to reorientate this in your books a little bit. So I'm going to have another triangle, and I've got my mass, my GFM, and my moles. Now, once again, I've got my GFM because I know what this is. Now, this is really important. That molar ratio does not affect the GFM. The GFM is simply calculated from the number of atoms that you've got in the molecule. The molar ratio is something that's laid on top of it later. So that number there is not ever included in calculating the GFM, and that is something people go wrong with a lot. So my GFM is just what that molecule of oxygen is, and we already worked that out to be 32. Now, I don't have the mass, so that's my question mark. But now, because I know the molar ratio and I've applied the molar ratio, the number of moles that I need is 1.5. So I'm going to do a backwards tick and put 1.5 in there. Now, this means all I have to do is multiply the moles by the GFM. So that is going to be 1.5 multiplied by 32, which gives me 48. So 1.5 times 32 equals 48. Now, what's important here is that the mass is always given in grams. And I'm going to double underline that because that is my final answer, and that's the number that I want them to mark. So 48 grams of O2 is required for complete combustion. Now, this is a pretty in-depth example. Once again, these things you're going to have to work with, and what we've done is a pretty complicated example. It's using pretty straightforward reactants. It's certainly something that you should have seen before, especially if you've used a Bunsen burner. This is really what you're looking at. This exothermic reaction producing carbon dioxide and water, and our reactants are methane and oxygen. Our products are always on the right hand side. Our reactants are always on the left hand side of that arrow. I appreciate that was a pretty hefty little lesson probably for most of you. What I want to do is just give you a question now, and this is going to be the task, is to work through this question and see if you can manage it. There will be questions about this. This is definitely something that in a normal week we would have probably have done this experiment, and we would have spoken about it. We would have done a couple of starters and things involving moles, mass, and GFM. But I think this is probably the most straightforward way to do this. So what I'm going to do is write you out a question, and that is the task for today. Okay, so you should definitely feel free to ask questions on Teams, and please work with people. It will be important that you chat about this and discuss it. So, first of all, we have got sodium and chlorine. This is actually a really cool experiment that we could technically do in school, but chlorine gas is quite dangerous, so we tend to avoid it. It gives you a really nice bright light when it happens. And we get salt formation, so we get sodium chloride. And what I'm asking you to do is, if I gave you 7 grams of chlorine, how many grams of sodium would be required to react fully with that chlorine? It is essentially the same question, but you're going to need to do it yourselves. Tips: balance first, then find your relative atomic masses, which will help you figure out the GFMs, and then use your equations to see if you can work it out. Admittedly, I've chucked this in quite far at the deep end. My understanding from most of the people in the Nat5 group, at least the ones that I have taught, have done molar calculations before. So this is probably at the deep end of the pool a little bit, but I think it's a good place to start, and we can always track back and we can do some simpler examples if people are finding that they're struggling with that. You've got access to the video. Rewatch bits and pieces of it. Try and follow the line of thinking through. All of this is about turning some of these pretty new concepts and skills into long-term memories. Right, good luck with that. Post your answers up on Teams, and I will post the answer to it in probably after the weekend. My internet has been chugging along at a very slow pace the last couple of days since Monday, so I'm not quite sure how long this will take to upload. The advanced hire stuff has taken over 4 hours this morning, so it is looking like this is probably going to be put up by the afternoon, so should be good for after the weekend to have the answers in for this. Any questions, put them up on Teams.